Welcome back to the Aether Vector. I'm Lewis Maverick Adams, your guide across the frontier where machine learning meets human intuition. At our think tank, we scan the horizon for global shifts. In our labs, we prototype solutions through our fun. We deploy capital. Today, we're putting on a different hat. We're storytellers, translating dense theory into everyday language. We'll uncover why explainability matters, how to wield it, and what it means for you. Imagine we're walking through a gallery of AI models. Some are glass boxes, other are opaque sculptures. I'll point out their features, and at the end of each segment, a short visual will appear, just long enough to reinforce what we've discussed. Our mission? To turn the black box into a glass house. Let's start with why this matters. Artificial intelligence and machine learning models are increasingly used in high stakes domains. AI systems are making credit decisions, diagnosing illnesses, and guiding investment strategies. Yet most of these models operate as black boxes, complex functions spitting out scores without telling us why. That opacity erodes trust. In intensive care units, clinicians report that they can't rely on AI recommendations without clear rationales. Regulators are taking notice. The EU AI Act obligates high risk systems to provide transparency so users can interpret outputs. In the United States, a patchwork of state laws has prompted the White House to call for a national standard. Explainability isn't just nice to have, it is the bridge between innovation and accountability. This podcast is designed for a broad audience: tech savvy professionals, machine learning practitioners, regulatory and compliance officers, product managers, and business executives. We'll ground our discussion in theoretical frameworks and then we'll transition to practical applications, case studies, and tools. There will also be visual elements where we sketch simple diagrams to demystify key concepts. Welcome again. When we talk about explainability, we're really asking, how can we understand why a model made a particular decision? How do we make sense of this space? We can think of explainable AI along four dimensions. The first, intrinsic versus post-hoc. Some models like decision trees and linear or logistic regression are transparent by design, meaning you can read off how each feature influences the outcome. They trade some predictive power for clarity. Black box models such as deep neural networks, gradient boosting, and random forests require post hoc methods to explain them. Two of the most popular are LIME, local interpretable model agnostic explanations, and SHAP, Shapley additive explanations. LIME fits a simple model around a specific prediction to explain it. SHAP uses game theory to assign importance values to features. SHAP can be computationally intensive and depends on the dataset, while LIME is faster, but may be sensitive to how you perturb the data. Then there's model specific versus model agnostic. Some explainers peek inside the model's architecture using gradients and activations to highlight what drives the prediction. Integrated gradients and GradCam fall into this category. Others treat the model as a black box, relying only on input output pairs. Lime, SHAP, permutation importance, and partial dependence plots are model agnostic. Then there's local versus global. Local explanations answer, why did this specific prediction happen? Think of a loan decision or a cancer diagnosis. Global explanations tell us the overall behavior of the model across all data points. Counterfactuals, Lime, and SHAP operate locally. Permutation importance and global surrogate models reveal global patterns. For regulatory audits, you need both. Local explanations satisfy individuals, whereas global analyses identify systematic biases and support fairness audits. Counterfactual and example based explanations is the next one. A counterfactual is a what if scenario. You were denied a loan because your annual income was $30,000. If your income had been 45,000, you would have been offered the loan. This form of explanation doesn't reveal the model's internals but gives actionable insights. Example based explanations like retrieving similar past cases help contextualize predictions. To help visualize these dimensions at the end of this segment, we'll show a matrix positioning techniques along the intrinsic versus post-hoc and local versus global axes. You'll see where decision trees, Lime, SHAP, GradCam, and global surrogates sit. Let's get our hands dirty. SHAP and Lime are household names. SHAP values derive from cooperative game theory, attributing to each feature its contribution relative to the average prediction. This makes SHAP consistent but computationally heavy. Lime perturbs the input around a single observation and fits a simple model. It's lighter weight and intuitive, though its explanations can vary with the perturbations. In practice, you might use SHAP for critical, high stakes applications, and Lime for quick debugging or prototype exploration. Visual methods like GradCam and integrated gradients overlay saliency maps on images or highlight influential tokens in text. Clinicians need these to ensure AI models focus on plausible features. Surrogate models such as simple decision trees or linear regressions trained to approximate a complex model provide global insight. Counterfactual generators such as Alibi and Dice propose minimal changes that flip a prediction, empowering users to act. Let me share two scenarios. First, imagine you're building a credit risk model. You train logistic regression, random forest, and gradient boosting. The gradient boosting model performs best but is a black box. You deploy SHAP to explain why it denied a specific borrower. The SHAP bar chart reveals that the person's checking account status and loan duration push the risk score over the threshold. Now you can communicate this to the customer and regulators with confidence. Second, step into the radiology lab. You're using a convolutional neural network to detect pneumonia from chest x rays. Clinicians are skeptical. You apply GradCam and see that the model focuses on the long field rather than irrelevant artifacts. Trust increases. This interplay between model and human highlights why saliency maps are more than just pretty pictures. Across industry, the stakes vary, but the need for explainability is constant. In healthcare, a 2025 review of over 1,000 AI enabled medical devices found the average transparency score was just 3.3 out of 17, and that nearly half of the devices didn't report any clinical study or performance metric. The FDA's Good Machine Learning Practice Guidelines stress the importance of providing clear information on model performance and data sources. In generative AI, researchers highlight generalization issues, computational inefficiencies, and trade offs between interpretability and performance. There are no standard evaluation frameworks yet, making this an area ripe for exploration. Regulation shapes how we build explainable systems. The EU AI Act sets clear timelines. It entered into force on August 1st, 2024, and will be fully applicable on August 2nd, 2026. Best practices and AI literacy obligations begin on February 2nd, 2025, and obligations for general purpose AI begin on August 2nd, 2025. High risk systems and regulated products have until August 2nd, 2027. In the US, the absence of federal standards has led to a patchwork of 50 state regimes. In 2025, White House executive order calls for a minimally burdensome national standard and directs the Attorney General to challenge state laws deemed too onerous. And meanwhile, the FDA encourages clear disclosure of model performance and data sources, and the EMA and FDA guiding principles urge human centric design, adherence to standards, multidisciplinary collaboration, data provenance, and risk based performance management. These policies are not static, they evolve with our collective understanding. Staying ahead means anticipating requirements and embedding explainability from day one rather than retrofitting it after regulators come knocking. So, how do you take these ideas from podcast to practice? Here are a few principles. Start simple. When possible, choose interpretable models such as logistic regression or decision trees. If performance demands complexity, pair your model with XAI tools like SHAP, Lime, and surrogate models to eliminate both local decisions and global patterns. Tailor your explanations. A loan officer might want a SHAP bar chart, an executive may prefer a high level dashboard. A clinician needs a saliency overlay. Speak the language of your audience. Integrate governance, maintain audit trails, monitor performance across demographics, and include humans in the loop review for high risk decision. Keep learning. Regulations will evolve across the EU, the US, the FDA, and the EMA. Invest in cross functional education so data scientists, risk officers, and executives can co create responsible AI. You've just walked through the landscape of explainable AI, from intrinsic black box models to post-hoc explainer tools, from credit risk dashboards to radiology labs, from EU regulations to US patchwork. We learned that gradient boosting models may outperform others but require SHAP to meet transparency obligations. That clinicians trust AI only when it communicates the origin of its results, and that most FDA approved AI devices still lack basic performance disclosures. We also saw that generative AI adds new complexities with no standard frameworks. The takeaway: explainability is an ongoing dialogue between humans and machines. It's a strategic imperative, not a checkbox. As we wrap up, I invite you to put these ideas into practice. If you're part of our Aether Vector community, join us in the labs. Build a credit risk model, run SHAP, draw a saliency map on an X ray, and generate counterfactuals. If you're in the think tank, consider how these concepts shape global shifts. If you're in the fun, evaluate startups through the lens of explainability. The visuals we've promised will follow. Our matrix and comparison table will provide a quick recap. Thank you for joining us here at Ether Vector. Until next time, this is Lewis Maverick Adams, encouraging you to turn every black box into a glass house.